Hi, Grace.
Hi, John.
Hello. How are you?
Good, good. Are you doing the system? It'll be a lot more today. Can you switch it? Yeah.
Wait, I can't understand your words. Somehow it is distorted.
Mm, never mind.
Okay. How was the exam? How was it? The final exam for Python.
Stressful for sure. But I spit something out.
Hi, John. Hi, Grace. Sorry for being late. I extremely apologize. I was
No,
on a
sir.
meeting with Yasmin, and we were talking about this funding that we got, and I lost track of time. So again, I apologize for being late. Um, how are you guys? How's the exam? The exam in Python? Find it very easy. Like, was it like a walk in the park?
It
Grace,
was tough.
Grace?
It was, it was tough. I think it would have been nice to have an objective.
Yeah. There were parts in there that we failed to cover in class that I think, well, you have to know, but we'll be using them in the statistics part. But yeah, there will be times that you really need to search the internet for answers. That's a given reality. You can never you can never remember everything. There's just too much information.
I'm good. Thank you.
Hasiba, how about you? How did you find the
Hi,
exam?
hi everyone.
Good.
Um, the exam was tough
Mhm.
for me uh, because I think we didn't had time to practice,
Okay.
uh, especially the last part.
The last part? Yeah, I
Yeah,
agree.
so yeah, it wasn't easy. Although we used AI or
Mhm.
ChatGPT and some videos, but still.
It won't give you
It
all,
was not
right?
something that I could do by myself. It was like
I see,
depending
I
on
see.
something.
Yeah. So, yeah, that exam was really built to really stretch you. So I agree that even if you browse online, use AI, there's a programming part in which the AI could help you, but the analytics part is something that you really need to think about, right? You have to apply your critical thinking skills in that part because okay, um you imagine that you're already the data analyst of that company, that superstore grocery, and you would be thinking, okay, what does the company need? What does the company want to answer? Okay, so what is the impact of this recommendation that I got from the analysis? Is it realistic? Is it something intuitive? Because oftentimes the results that will be coming from your analysis, from your data, would be unrealistic. So you need to make sure that you validate it with reality. Is it really realistic? Is it something that can really be done? Okay, so those kinds of things, those scenarios, you need to be familiar in how to handle them. So I want to share this experience when I was still part of the university here in the Philippines. I was part of the planning team, and most of the time people would be presenting their work um, with a board of directors, board members, and they would be they would be presenting this findings from the study, the model that they built. Oftentimes, those models that they built doesn't really reflect what's happening in reality on the ground. So sometimes we are very how should I say this? We are fixated with a perfect model, with a perfectly looking model, based on different metrics, but we fail to validate if it's actually what's happening on the ground, or if it's something that is really reasonable. Okay, so that's something that you need to develop aside from programming. That's something that you cannot just search from the internet. You cannot just ask AI to do that for you. Okay, it will take a long time for AI to develop that skill. Okay, so for the next 3 to 4 weeks, I think 3 weeks, it would still be Python, but our focus would now be on statistics. So why is it important? Why did we include statistics in this course? Because typically, if you would look into other programs, similar boot camps, you won't find any boot camps that offer statistics as part of their DA course. The reason for that is, um, we observed that with junior data analyst position, they're just focused on their training about the tools. Okay, they think that it's already sufficient for them to know Excel, to know SQL, to know Power BI, and Python, but you really need to know how to analyze data. What are the methods available for you? Okay, so that would give you an edge. That would give you an edge over the competition. They just know how to use the tools, but you know how to analyze data through statistical methods. And you're at the middle point between being a data analyst and being a data scientist. Okay? In this section about statistics, we will not only learn how to use and what statistical methods to use. We will also understand why they are working. What are the inner workings of these methods? What do we mean by A/B testing? What do we mean by when we do analysis of variance? What do we do when we do predictions using regression analysis? What do we mean by p-values? Those kinds of things. It's important for you to know that, because that's the language of data. If you want to be a master of data, then you need to know statistics. Okay, so that's what we'll learn for the next 3 weeks. And your exam would still be in Python, and would still be on a similar setup as what you've done um, recently. So it would still be a data. I'll be giving you another data. This time it will be tougher, because the data set would be an actual data set from an actual survey. Okay, so um, it would be I'll be injecting more um, problems into it. So you need to perform more processes of data cleaning as compared to what I gave you with Superstore. I think it's cleaner, but it's not the case with actual data. You have to really invest more time in data cleaning. So that's what we'll do. This would still be Python, but Python, or rather the other way around, statistics with Python. Okay. So for this first
I
lecture,
check.
I'll be focusing more. John, I think. Let me meet John for a while. So for this first lecture, we'll be focusing with the types of data. What do we mean by an ordinal level data? What do we mean by um, a nominal type of data? Because again, I think I've mentioned this couple of times in the past. The type of method, the type of analysis that you will do on a data depends on its level of measurement. So it's not a one size fits all kind of thing. It's not that you've identified a method, the just because you know it, you'll apply it to everything. No. So there's a question about validity. Is it valid to apply a specific method to this kind of data set? So that's what we'll understand in this first lecture. And by the way, before I proceed with the details of the lectures today, I have few announcements. So you don't have any classes on Thursday. Uh, was it Thursday? It should be Friday. No. It should be Thursday, Friday on my time, because of Independence Day, right? And you also don't have any classes on Saturday. So it was designed that way so you enjoy the long weekend. It's not from me, it's from the admin. So all of the students in Skillspire, they have long weekend this coming weekend. Okay? So it's something that yeah, you should take advantage of. I will not be giving you any assignment that would be needing to done during the weekend. I don't want you to hate me, but we'll maximize the time for this first lecture and the second one. So I want to cover the most of the topics that were planned for this week. Okay. So any questions before we start? Grace, Hasiba, Jeff, and Anissa just sent a personal message to me. You just sent. Okay. No questions, guys?
Right now, back to LA, so I'm gonna be listening in. I won't be able to participate in any exercises actually today,
Sure,
unfortunately.
sure, Jeff. Keep safe, keep safe. Thanks for letting me know. Okay. If something is confusing, you can use the time tomorrow to clarify it with John. John is a statistics major, so I can assure you that everything that we'll be discussing now in the next few weeks, he is 100% knowledgeable of that. Okay. So I think enough of the talk, and let's um, start the discussion. They say that oil or data is the new oil, right? Every company, every organization, they want to know how can they make use of those enormous amount of data for their advantage, whether it is for profit or not. They want to do smart decisions. And that's the reason why statistics is needed, because it allows us to unbiasedly arrive into smart recommendations for organizations. What do they need to do? And what are their expected results? Okay, so that is very useful for leaders. That's why you would recognize that those on the upper echelons of organizations, those are people that know how to deal with data, because of these leaders need advisors. Okay, and it's a proven fact. Now, if you go back to history, those Khans, if you know if you're familiar with the history of Genghis Khan, if you go back to ancient Rome, this leaders, they had advisors. This advisors, they use information from different sources um, that allows them to provide this recommendation. Sometimes those recommendations are not free of bias, especially during those times in which this methods were not really present, or um in a it's not even scientific during that time. Okay, so but now in the age of information, I think, yeah, it's correct. Ignorance is a choice. right? If you want to learn something, if you want to decide on something, you have the information through the internet. You can check. And you should be careful because there are erroneous information that you can find also in there. So this statistics for data analysis lecture would be focusing on three things. Okay, what methods should we use on a particular data type? How should we do it through Python, and why is it working? Those are the three uh, focuses of this discussion. It's not, again, it's not sufficient that you know something. It's better that you understand it. Okay, so let's move on. Okay, and just like that, my okay, my computer is acting up. It's frozen. Okay, it's already white. No. Do you see it? It just froze, and I hope it doesn't delete my slides because I would be freaking out if it does. Okay. Okay, I hope you can see it again. Okay, so what are today's plans? For this first lecture, it will be overview of statistics and its relevance in data analytics. So it would be understanding the role of statistics in data analytics and the basics of statistical analysis. Definition and importance of statistics, applications of statistics in various fields, how statistics aids in decision making and problem solving. And I'll be introducing some statistical methods to you, but at this point, it's just for you to be familiar with them. We will have a dedicated session, I think on the third week, that talks about everything that you know about this typical methods that's being used in data analysis. Okay, I want to make sure that everything I know I will be able to transfer to you. Okay, now let's define statistics. I want you to give me an idea based on your understanding and based on your belief. What is statistics? Hasiba, what do you think of when you hear the word statistics? Or how do you view how do you define it in your own words? Hasiba? Okay, I think Hasiba is away. Grace is working. Okay, there we go, Hasiba.
So I think of mathematics
Okay.
when it comes to statistics,
Statistics?
maybe yeah,
Mm-hmm.
analyzing data,
Mm-hmm.
uh, uh, who related to math. I don't know.
Correlated to
I
maths.
feel
Okay.
like yeah, mathematics. Yeah.
Okay. Yeah, I think that's a typical view uh when people hear about statistics, they are thinking of maths. But mathematics is different from statistics. We cannot say that a mathematician is also a statistician and a statistician is also a mathematician. It's like physics and maths. Okay, maths is a tool for physics. They are completely separate thing. Okay, it's not sufficient for you to know how to navigate, solve equations, uh, and it's already an assurance that you'll be a good physicist. It's not like that. It's similar to statistics. It's not an assurance that you're good at math, then you'll be good at with stats. Okay, they are two different entities, but both physics and statistics, they are using ideas in mathematics. So in statistics, everything revolves around data, information. You give me set of data. Now I have methodologies. I can develop methodologies that would extract insights from it. Okay, it could be an unstructured data that would be beaten to the pulp to get the essence, to get the insights from it, and eventually, ultimately, formulate plans, recommendations out of it. So, in a sense, I believe, well, this could be a biased, well, belief are oftentimes biased, but um, I feel that statistics is more related to reality than mathematics. Things could be very counterintuitive as you proceed with higher mathematics. I assure you that, especially when you are working with, uh, for example, theory of numbers. Some things don't really relate to reality. Okay, some things are really counterintuitive, especially in the pure mathematics case. But with statistics, it's very useful. Okay, as compared to pure mathematics, it's very useful. You take information, a set of input, you process it. So the process would be apply this methodology, and the output would be a recommendation. Would you go with this plan? What is the expected result, and what is the level of confidence that you will get that result? In statistics, there is no assurance, or there is no 100, not assurance, but there is no 100% fail proof option. Okay, there is also a degree of error, but we are able to quantify it. We're able to measure it. Okay, in that sense, you are guided with whatever your decision is. You have this probability of committing an error that is equivalent to this kind of loss. Okay, and if, for example, a company is choosing, okay, uh, uh, different alternatives, you can provide, okay, if you go this route, this would be the probability of success, and this would be the equivalent benefit. If you go to the other route, this would be that and that. You can only arrive to that, okay, to those conclusions, to those recommendations, if you know how to navigate and understand data. Okay, and there are things. This is quite surprising. Oftentimes, the belief of people, their personal biases and their inclination to things actually violate what's being, what's really going on. It really violates. Like, for example, give you a concrete example. The pandemic. Okay, during the first few months of the pandemic, some people not believing on its existence, but people are already dying. I mean, what is the probability that that virus is not real, given the fact that people are already dying? Uh, this number of people are already dying due to the same findings. That would be extremely improbable, right? The probability of that would be very low. But people, they have this sort of convoluted um, thinking. They tend to how do you call this, justify their beliefs, and that's what we want to eliminate when we decide things. We want to make sure that we separate people's belief, people's inclination and biases towards one thing. Okay, we want only the truth, and that truth can be extracted from data. Okay, the data doesn't lie, at least in most cases. Okay, we can make it lie. I mean, I have I have received couple of asks before about the research, because they want to identify significance. Again, if this violates the, the entirety of the reason why you do research. But there is this belief in the research community that if you don't find any significance in your findings, then your research is a failure. Of course, that's not the reality, right? But what I want to tell you is that we can make it lie. Okay, since we know how to navigate, how to um, bend it. Okay, how we know how to bend it as data analysts and knowing statistics, we can make it lie. Okay, so you must have a trained eye to see the issues with the data with a result of an analysis. So to define statistics in a more formal way, I've included it here. So let me go through it. Statistics is a branch of mathematics. Okay, it's a branch of mathematics. It's not mathematics itself. It's only a branch of mathematics that deals with what? First, data collection. We will be talking about different methods of data collections under the two subsections of it, probabilistic and non-probabilistic. And we'll be discussing, okay, what would be the repercussions if you do non-probability data gathering or non-probability sampling? What would be the repercussions if you um, do sampling with a stratification? Those kinds of things. We'll be discussing that on Wednesday. And then here comes the analysis. There are tons of analytical methods, tons of them. Okay, but do we need to memorize them? The answer is no. Okay, we have to be familiar with them, but we don't need to memorize them. What identifies the method is, again, well, first is the level of measurement. Is your data categorical or numerical? Okay. I think Grace got dropped out, and I can seem to onboard her. Let me. Okay. I think. There we go. Okay. So yeah, we will be talking about those. Okay, about those methods uh, for analyzing categorical data, for numeric data, but not all. Again, it's impossible for us. It's impossible for us. Okay. It would take you even a 4-year course in statistics would not you would not be able to cover all of them. Okay, all of the statistical methods there are. So um, statistics involves the study of methods for collecting, analyzing, interpreting, and presenting empirical data. So the presentation is part of the subject of statistics. And if we fail to cover that in the Python section, we'll be covering it here in the statistics section. How do we use Python to do data visualization? So we will be using 3 libraries for this: Seaborn, Matplotlib, and I'm thinking about Plotly for interactive dashboard. You would love it. I'm not I'm not investing so much time. Well, I did not invest time discussing it during the Python session because I know it will be covered in the statistics part. And we also have Power BI for that topic. Okay, so it provides tools for understanding patterns, trends, and relationships within data. Okay, so unfortunately, time series analysis would not be part of this lecture because um, we need to be solid when it comes to foundations in order to understand time series analysis. But we can do um, basic computations, for example, moving averages. I think that would be possible for us to discuss here, and some other techniques like determining seasonality and so on. So it's just pattern detection after all. So by transforming raw data into meaningful information, statistics help us to make evidence-based decisions. That's the key, evidence-based. We're eliminating biases and those uh, inclination that would screw up our decision making. Now, what are the applications of statistics? Statistics can be applied in almost every field. Statistics can be applied in archaeology. It can be even applied into um, quantum physics. They derive this. There's a section in quantum physics such called um, I forgot the section, statistical um, mechanics, something like that. It can be applied to business, of course. It can be applied to education, almost every field. I couldn't think of any field that doesn't use data. If it uses data, then it uses statistics. There might be differences in the terms, in the terminologies, but they're typically referring to the same, like for example, same concept in statistics. So recently, I got um, uh, a client that has a research about bamboo structures, and he mentioned about surface pressure modeling. And when we had the meeting, that modeling procedure only uses regression analysis, which is I should say a classical method in statistics. So typically they have this different terminologies for the same stuff in statistics. So that's civil engineering, structural designs. And yep, healthcare, of course, epidemiology, clinical trials, the way they identify the efficacy of drugs, of vaccines, they do that using statistical methods. And with epidemiology, you can model the rate in which, for example, a virus is being transmitted, given certain parameters. Public health studies, of course, and um, for the government, you have the policy making. Apologies for the typo there. So for policy making, I think you don't want to do trial and error in policy making, right? Every policy must be studied well, must be backed by evidence, like empirical evidence, um, so that it would be it would be effective and will not be ruining people's lives. So, of course, academia and research. I think this is the typical route of statisticians, um, and they typically apply statistics in doing research, right? Hypothesis testing, and so on. And let's proceed to role of statistics in analytics. You might be thinking, this is a coding boot camp. Why do we have that? This again, it's not sufficient that you only know how to use these tools, because you won't have any competitive edge over the other applicants if you just know the same things as with them, right? So knowing the language of data, knowing how to navigate through it, understanding the intricacies of this method would allow you to have that competitive edge. Okay, so it's the process of examining data sets to draw conclusions, provides the foundations for data analytics by offering methodologies for data collection, analysis, and interpretation. Before, um, it is synonymous to call statistics as data analytics. Maybe 15 years ago, they are synonymous. You say statistics, you say data analytics, you're pertaining to the same thing. Now, with the advent of these different technologies, they kind of created a separate section for data analytics. It's more now related to IT, to programming and these tools. But before, when you speak of data analysis, you are pertaining to this. And even with data science, there's no term data science before. Okay, I think Harvard sort of how do you say this? Um, made the term famous. They call data science is then like the sexiest job of the 20th century. So before 20 years ago, 15 years ago, you can find anyone that calls themselves data scientist. It's either statistician or analyst. Okay, but it evolved. I'm not saying that it's a bad thing, but I'm just saying that everything, data science, data analyst, all of those are just statistics. Even AI and machine learning, you won't believe me. Those methods that they're using there came from statistics. Those are just all statistics. They just gave them fancy names. Okay. They combine the idea of statistics with technology. That's how you train the machines to learn through penalty and reward. Okay. You feed it with 1 billion rows of data set, learning the patterns, learning the trends, and you cannot do that without this good technology, this fast computer that we have. That's why Nvidia got really the Nvidia shares got really high because of generative AI. But at the core, what they're doing, what the methods are what the methods that AI, well, this AI systems are using, they're just statistical methods at the core. Now, we do have two branches of statistics: descriptive and inferential. So descriptive is just mainly describing your data set. So I give you a data set, you describe it, summaries, um, you look into correlation of values. Those are descriptives. However, there is this more interesting branch of statistics called inferential. So it makes predictions or inferences about the population based on a sample. So oftentimes it's more efficient to just study a sub of a totality, because one, it is just impossible to take every part of the totality as part of your analysis. It's just impossible for so many reasons. The second one is it's less expensive to do that. It's less expensive to try getting all of the members of the totality, or what we call population. It's very expensive to do that. And third, most of the time you'll be injecting so many errors when you force it, when you're forced to get all of the members, just like during census, right? With census of the populations, it's not really possible to have an actual count. There are just estimates with some degree, like 1% degree of error, margin of error as they call it, right? So with inferential statistics, you try to understand the totality through its part. When you go to a doctor, you're not feeling well, in order for you in order for you to identify what's going on with your body, you'll be needing to have blood samples, right? And imagine if the doctor needs to drain all of your blood to just understand what's going on with your body. You'll be dead, right? Put it simply, it's not possible. But since your blood is mixed, right? It's I should say equal mixed, not perfectly. Whether you take a blood sample from your toes or your fingers, the finding would still be the same, right? If you have diabetes, then whether you take it from your finger or through your toe, then it would still tell you that, okay, this is the composition of your blood and you have diabetes. So it's the same principle. You don't have to get all of the members of the population in order to understand the totality. You can just take a part of that. And that's what we'll be discussing next meeting on Wednesday. What are the methods? Because we want to eliminate bias, right? There could be biases that could arise from the collection of data, and we want to avoid it as much as possible. So that's the inferential part. Predictions, like how do this weather forecasters, right? How can they predict the route of the typhoon? How's that even possible? With computer simulations, it's not it's not a very long time since we were able to do that. It's like couple of years. I think it's like 30 years ago that we were able to predict like for 4 days the route of the typhoon. I forgot the name of the uh, scientist that developed that. But the funny thing was that that ability was first thought or developed to predict stock market. So it's then all for profit, all for money. And then this breakaway scientist, okay, instead of applying it for profit, we just well apply it to climate because it's also like a chaotic system, and many would benefit from that. Imagine um, you can prepare before the typhoon hits your place because the scientists were already aware that based on their model that that typhoon would hit your location 4 days from now, right? So, or 4 days after. So it gives you sufficient time to prepare, and thus we're able to reduce the casualties from those typhoons. So that's one of the benefit of inferential statistics. And yeah, if you're on the financial industry, you can do predictions for like CPI, right? Inflation reports. You can benefit from that if you're really good. But of course, there's this. If you're familiar with the EMH, efficient market hypothesis, so there's no perfect model. So enough of that. Let's move on. Okay, and you can interrupt me anytime. Maybe you want to add something in your field in which statistics is being used. Anyone who wants to add? Do a quick discussion about how statistics being applied in their field. Okay. So lecture number 2, types of data, categorical and nominal, or numerical, I should say. So data can be categorized into different types. And it's always important to ask yourself this. Hmm, you're given a data. The first thing that you have to ask yourself is this categorical or numerical? Because if you're thinking of creating a visualization out of that data, it also depends. That visualization also depends on the data type, right? Right. So it's important to ask yourself that, okay? What data am I working with? Understanding the type is fundamental for selecting appropriate statistical method and analysis techniques. Okay? Okay. Let's talk about categorical data in much detail. Categorical data, also known as qualitative data, represents characteristics or attributes that can be grouped into categories: nominal and ordinal. So nominal or data, those are categorical data with no inherent order. There's nothing, okay, that tells that group A is better than group B inherently. Think of it about like gender, right? Inherently, there's nothing that tells you that males are better than females or the other way around. It's nominal in nature. It's just a way. The category is just a way to group to group uh, the inputs. Ethnicity, right? There's nothing that would tell you that a particular ethnicity is better than the other inherently. Okay, it just varies. You might be thinking, okay, these people, there's this, I think, thinking about Asians, right? They are typically viewed as intelligent, extremely intelligent, extremely short people. But In reality, there are certain factors that made them to look that way. Maybe their food, maybe the climate, right? And maybe the in terms of education, the system. But all in all, if we try to eliminate those differences in parameters, we're all humans. We're all the same. We're all the same. If you try to u- uniform those parameters, those environmental factors, those diets, and so on, we're just the same. That makes you wonder why um there's this how do you call this? There's these issues about race, right? We're all humans. We're just the same if you remove those factors and you observe it across time. There's really much difference at all. Okay, so we have ordinal data. The next categories with meaningful order. So there's an inherent ordering between the categories, like educational levels. So you start first with primary or pre-kinder, primary, secondary, college, graduate school, and so on. There's an inherent ordering. There's a hierarchy between the categories. Ranking. So can think of sizes: small, medium, large. Small is smaller than medium, medium is smaller than large, right? Large is larger than medium. So there's this inherent ranking or ordering based on whatever characteristic between the categories. That's the difference between nominal and ordinal. You can think of it this way. Okay, your address. What is that? What is the type of that uh, data? Your address. It's qualitative, so we can classify it as categorical, even if there's number in it, right? So your house, it doesn't have an inherent like difference or ranking as compared to the other house. It doesn't mean that if you're number 3 and your neighbor's number 4, the neighbor's house with number 4 is bigger than your house. It's not like that. Okay, so your address is a nominal variable. It just identifies your location, your house's location. However, it's different from ordinal. If you think about the ordinal as like the result of a race, you have first, second, and third. So the difference is the amount of time spent in reaching the finish line. So the first would be, well, the very first one to reach the finish line, then followed by the second and third. Okay, so there's this ordering. That's the easiest to spot the difference between a nominal and ordinal data. Is there an inherent structure? Is there an inherent ordering, hierarchy between the categories? If not, then it's just nominal. Okay, can we convert a nominal data to make it an ordinal data? We can inject a characteristic, like in terms of strength. In terms of strength, generally males are stronger than females. So that converts it into an ordinal type. Do you follow? So you can actually um, convert one form into the other depending on the data type. Like for example, age. Age is a ratio variable, right? Age in years. Okay. I haven't introduced yet the ratio or any numerical type, but it's a different type of data. But you can convert it down to ordinal by creating the ranges, okay, and assign values to that, like young, old, and or whatever characteristic that you can assign to it. Give me a second. Okay. Okay, so let's proceed to some examples. So in fact, you already did this in your previous sessions with during the Python session, but I'll be giving you another example here. Okay. I'm gonna open my Colab and show to you some analysis that you can do. Again, this is not all. Just to give you an idea, okay, you have a nominal type of variable or an ordinal type of variable. What can you do with it? Give me a minute. Where was it? My computer is behaving oddly today. Okay, where was it? Okay. Zoom this a bit. Let me just copy this. Okay. Because I don't want to waste your time looking at me copying that thing. I'll just copy and paste all of that to my Colab. And okay, it doesn't allow me. Okay. Something's wrong with my computer. I can't even drag this. Okay. Okay, there we go. Okay, so basically here, I just want to show to you, well, things probably you already know because you've used it in your exam last week. So with categorical variables, oftentimes the first thing that you want to do with them is to generate descriptive measures. And what are the descriptive measures that you can do with them? Counts, right? How many are belong to this category? How many are coming from this group? So that's basically what we're doing here. So this is just a data frame, right? Currently, this is like on a library setup, then converted to a data frame through data frame pandas, right? And then I just extracted here the value counts, and then here I extracted the mode, and the mode is like the most occurring category, right? And if you run this, you'll just basically see a table that would show the counts. I hope it runs. It's taking some time. Okay, it's connected to the server. Boom. So there we go. So as you can see, this is the count, right? The counts for each of the color. So it came from here, and then the mode, the one with the highest number of observation, is actually red. So that's why red is being shown here. So typically, this is what will you do with um, categorical type of variable, particularly with nominal. You don't you don't want to generate numerical measures from it. Like for example, you recoded these colors like 1 for red, 2 for blue, 3 for green. By that, by doing that, you can generate numerical measures, right? However, those numerical measures doesn't mean a thing. Like for example, you generate a mean of 1.3. What does it mean? It means nothing because in the first place, even though the software allows you to compute for means, inherently you must not do it because you just recoded the inputs, this numerical variables, into codes for the purpose of first make ease of coding, right? Or plug it in as an indicator variable in your model. But you don't you may well you must remember that you should not generate summary measures for numerical variables for this recoded inputs. Okay, you will remember that. Okay, you should remember that people would recode this as 1, 2, 3, and so on for ease of coding, but don't generate, never generate measures for numeric variables from recoded nominal variables. Okay, it's a common mistake. University students are committing that. Early data analysts also commit that. If it's nominal, the only statistical measures that you can generate from it would be frequencies and or percentages. Okay, so that's what you can do with that. Now going back here, going back to our slides. Huh, okay. Now we have a chi-square test. Some read this as chai, some read this as chi, but in reality, the chi is really the um the Greek letter. So this is a chi-square test. So what is this test? Again, I'll just give you a preview of this. We will not go over the detail. Okay, there's a separate section for that. What I want here for you to see is that, okay, I have this categorical variable. What higher analysis can I do with it aside from getting frequencies and percentages? Okay. Now, the chi-square test can be used to determine if there's an association between two categorical variables, not necessarily nominal. It could be nominal, ordinal, ordinal, nominal, ordinal, ordinal, or nominal, nominal. But, okay, in general, it must be that you are analyzing two categorical variables. And what just happened? I think my video got cut out. Can you still hear me, guys? Guys, can you still hear me? I think something's wrong with my computer. Okay, sorry about that. It's been going on since this morning. I've I have restarted it a couple of times, but now anyway, going back here again, this is used in identifying association. Is it existing? Like for example, in terms of preference, like preference for K-pop, Korean pop music, has gender something to do with it? Are females more into K-pop music as compared to males? You can think of it as also in terms of nationality. You're comparing Filipinos and Americans, which are more into K-pop music, or the Americans or the Filipinos. So you can do chi-square test with that. Okay. So basically, what's going on here is there's this chi-square distribution that we'll be discussing next week. So chi-square distribution is a type of probability distribution that explains a phenomenon. Okay, what phenomenon? Let me show you this. Um, Wikipedia will do. So basically, you are trying to compare what should be observed and what should be expected. So this is the chi-square distribution. I will not go deep into the mathematics because you don't need it. You'll not be teaching in the university. You would just use it, okay, for your analysis. So you don't have to go through the mathematics of this. So um, this chi-square distribution, okay. So it it is a type of probability distribution that models the probability of occurrences of a particular type of phenomenon. Now, there are some variations of the chi-square distribution based on certain parameter called degrees of freedom. So as you can see in here, with different degrees of freedom, you would see a different type of chi-square distribution. It could be more flat, it could be more bumpy, and so on. But the area under that is still 1, corresponding to a valid probability distribution, right? So what we're trying to understand here is the probability of observing something similar or different, or no, is the probability of of the expectation similar to what we have observed with the data. I wonder if that's the correct, the best word for it. Okay, let me give you an example. Another example. Maybe the words that I chose in there are not the best. So suppose that you're trying to understand if educational attainment plays a role in whether a person would be successful or not. And you might argue, Jeff, educational attainment can be measured in terms of number of years in education. But in this example that I'm giving you, the educational attainment is categorical. Okay, for whatever reason, it's encoded as such. Primary, secondary, finished tertiary, or with advanced degrees. Now, the success here is this defined as their own perceived evaluation of themselves, if they are successful or not. So, if you would put it in a tabular form, okay, let's pull up Excel here real quick. I promised myself not to go deeper into it, but I think it's just really needed. But again, I promise you, there would be a much more detailed discussion about this method. It's just to give you a glimpse. Okay, so suppose we have this scenario. I hope this is so. We have success at the top. It would be yes or no, right? Merge. Where's merge? Merge. Okay. Don't do this to me, Excel. Where is merge? Merge. Okay. The current look of Excel is confusing me. Usually they have the name for merge cells in there. So this is yes. Perceived success. This is perceived success. Just to make things clear. And then we have level of education here. on the other side. So primary, secondary, uh, tertiary, advanced degree. Okay. So say we have 100 people. We sampled 100 people. And mostly, okay, say there are 30 that are primary, there are 40, there are, hmm, so that is 70. Let's make things a bit realistic because we know that most people would have secondary level of education and less with advanced degrees. So this is the count, and we will be distributing that. So if we want to say that level of education has nothing to do with the success, right? The distribution of the yes and no must be near proportional with each other. Must be the same, okay? But if we if we hypothesize that level of education has something to do with how a person perceive their own success, then we should observe that more yes would be concentrated in a particular type of level of education. Okay, so suppose this is one version. Let's assign it version one. Say most people said, okay, we're not successful because um, whatever reason they responded like this, right? Don't leave this one. And for the secondary, let's say uh, 27 and then 13. And then tertiary said, uh, let's make the 18 and 2. And then say 9 out of 10 said yes. So again, this is the distribution. This is the observed values. Okay, these are the observed values. Where did it come from? From your survey, from your data collection, okay, from the responses of your um, respondents. Now, I want to ask you, what is the scenario if we say the level of education has nothing to do with success? That the proportion of those who would say yes and those that would say no, okay, must be approximately equal. But if we say that yes, level of education has something to do with success, either they feel that because they don't have a higher level of education, they don't feel themselves as successful, or they don't perceive themselves as successful, then most would be concentrated to no. Most of the responses would say no. Or it could be the other way around, that because most of these individuals, they feel that um, because they have higher level of education, they feel more success. It would be on the other side. There would be more yes. So we're looking into those two scenarios in which the concentration is more on the yes or more in the no. However, one thing about chi-square statistics is it is called an omnibus test. It won't show you which direction is the relationship or the association. It would not tell you that the relationship is more into the no, unless you look into the frequencies. It would give you an idea. But there's what we call a post test called Kramer's V. Okay, Kramer's is a post hoc test for chi-square. What are the benefits of doing Kramer's V after you've identified that there exists a relationship? First, it gives you the direction, and the next thing it gives you the gravity or the strength of the association. Okay, so just to make things clear, if you identify that there's an association between success and level of education in this example, and you want to understand how strong it is, okay, and what's the direction? Are we inclined more to they perceived it as no because they lack, or yes because they feel that they um they perceive themselves as more successful because they have more um they have higher level of education, then it would be the yes. So you have to go to Kramer's week if that's part um of your question. That's part of what you want to identify. But basically, if there's no association, there's no evidence of association, we would see a proportional result um, in terms of the frequencies. We would observe, okay, that the expected is not much different as with the observed. Let me put that into writing. If there's no sufficient evidence of association, then the expected frequencies will not be will not differ that much as compared to the observed. Okay, Jeff, what do you mean by the expected? The expected refers to the null hypothesis in this case. We'll be talking about this hypothesis, don't worry. But basically, the null hypothesis of this is that there's no association between success and level of education. So that's our expected thing. And it means that the expected frequency must be proportional between yes or no. We don't see any inclination to one category. Okay? So that's what we do with chi-square statistics. And that is used for categorical variables. Okay? To see if there are association. Okay? And this is very useful. Imagine you're a marketing analyst, okay, even a marketing manager, and want to identify, okay, uh, uh, the, do colors affect the preferences between males and females? Do colors affect the attention span? Okay, attention span is a numeric variable, right? But you can categorize it. So has it something to do with whether the viewer is a toddler, a teenager, or an adult? You see, Coco Melon. If you look at the animation and the color of Coco Melon, you see that the eyes. Well, if you're familiar with it, well, you have kids, so I know you're familiar with it. They have big round eyes. The colors are extremely vibrant. Those are results of statistical analysis. They see that the attention span of kids are much longer if they have those characteristics. There's a psychological aspect to that I don't know, but the way um they validate it is what I'm familiar with, right? I'm familiar that they did that analysis through either this or another type of modeling, statistical modeling, but most likely this kind of analysis. So they looked into it. Okay, we have identified that it's significantly different to what we observe if they are just the same in terms of attention span. So we can conclude that okay, this big round eyes, this vibrant colors are more appealing to the eyes of toddlers, and we should do them in order for them to watch our cartoon. So something like that. Okay. Now let's do away with this and go to coding. So I have here a set of code for chi-square test. And we will be using in most of the lectures a library called sci-fi.stats. The sci-fi.stats, you need most of the things that you need in statistics would be here. And I would be giving you a link So it's documentation. Again, guys, you don't have to memorize anything. Okay? Just make sure that you're understanding what you're implementing. I'm giving you the link in the chat box, and you would understand. Okay, I think I got dropped. My team's just crashed. Okay. Um, I don't know what's happening. So I was supposedly sharing something in the chat box, and then I don't know what I clicked. But I'm certain that it's not the X button. So the link in your chat box, that is the link to the scipy.stats library. And that library contains everything that we will be using, not everything, but most that we'll be using in this series of lecture in statistics. So going back here, right? So this is the implementation of chi-square test. And let me switch to my Colab because I have it in there. So basically here, um, we imported pandas, and we already imported SciPy stats earlier, right? Mm, did I? If I get any error, then it means that I need to import it again. But basically, what we want to extract from this library is this chi-square contingency. That's what we have to use. So as you can see, there's a word contingency in there because you cannot do chi-square analysis without any contingency table. Okay, because if you look at the formula, if we go back to the formula of this, you would see that chi-square is computed by subtracting the observed frequency and the expected frequency. I will not go to the manual computation of this because it doesn't make sense to do that, at least in your case. But the idea that I discussed in here in the Excel workbook follows that. Again, what is the expected frequency count under the assumption that success and level of education are not related or associated with each other? And you subtract that to the actual cell that you have. If the difference is substantial, then you can say that that null hypothesis that there's no association between success and level of education could be rejected, okay, with some degree of certainty. So that's what is going on in here. That's why you have the contingency word in there. So let's explain this step by step. So here I'm creating a library that contains two keys, gender and preference, with the following values. This is just a preparatory step for creating a data frame, right? Because we'll just apply the data frame in here. Again, this is not like a required step to do because most of the time our data set would be in the form of a CSV file, and then we'll just extract the columns of that CSV is already in a data frame format, right? So remember the column slicing, the square brackets. You can use the excess, uh, the dictionary or the list type of method of accessing them. So it's your call. It's just this example. I need to create a data set. Okay, but I'll be giving an example in the third session, in the third week, rather, that okay, here's a data set from a CSV. How can we apply chi-square in there? So in order to create a contingency table, this is part of your exam, you can do a cross tab. Cross tab is a method of pandas, right? So if you tell AI, okay, I want to create a cross tabulation of gender and preference, then it will just give you this method cross tab from pandas. So basically, you have two variables in here, gender and preference, okay? And that is this. So male and female, female and male. And then here we're applying chi-square test. Okay, so this is the structure. If you go to sci-fi stat, this is the structure and how you will be implementing chi-square statistics. So always refer to the documentation if you in case forgot how to set this up. You don't need to memorize it. Just have your documentations ready. I recommend you to put it as favorite in your as a favorite in your browser so that anytime you need, you can go back to it. Just do Control F. It's like this. I'll be clicking on it, open my browser, and then there you have it. If you want to say sci-fi, I want to do cross tabulation or chi-square, so I can easily just click on that, and then there are this example that you can use, or just have AI do the structure for you, and that just um, um, structure it for your data set, right? So this is the guides that you'll be needing. Prior to GPT systems, this is how we do it. Like going through the documentation every now and then. Okay, if we encounter any issues. Now, so let's discuss the results here. So for this particular data set, the p-value and the chi-square value is this. Now, this concept is probably the most difficult aspect or the most difficult thing to grasp and understand in the entirety of the statistics discussion. The concept p-value. They say that if you understand the concept of p-value, then it's like finishing a one whole course in statistics, because even the the practicing scientists, those that are using it, they haven't really understood it at the fullest. The reason for that is oftentimes teachers, they interpret it in a very technical way. But let's think of it this way, okay? Let's think of the p-value as the probability that the null hypothesis is true. The null hypothesis is, in this case, there is no association between gender and preference. Okay, if the p-value is very large, the maximum it can assume is just one. That's the maximum probability value. You can go over one, right? Doesn't make sense. It cannot be negative because a probability 0 is an impossible event. It would never happen. And a probability of 1 is a sure event. That will happen every time. So going over that or going beyond 0 negative values doesn't mean anything, right? Now, here, if you observe that most of the yes, okay, is concentrated on the female, what is the probability of observing that statistic, or as extreme as that, under the assumption that if there is no association between preference and gender? Let's make this a bit larger. Let's imagine it like you have 1,000. Okay, I can do that. Give me a minute. I'll convert it into a thousand data set. Give me a minute. No, I can ask the help of AI here. I want the code above to generate 1,000 samples. Okay. Want this code to generate instead. Hmm, let me see. Uh, yeah, this is what I need. NP random choice. Perfect. That's what we want to add in here. So that random choice, it's applying the concept of binomial distribution so that it can generate thousands of observation in here. Let me see. Import numpy as okay, perfect. And NP random choice. I want to put more weight into the preference of yes. Let's see, NP random choice, NP dot random choice. By let's see. Uh, there we go. Size replace P is equal to none. I suppose that P refers to the weights that we can use, that we can treat uh, in order to generate more of where is it? Okay, there we go. It's an array. Okay. Now we can do that here. So P size. So it's after the size. Okay. So P. Okay. P would be an array that contains the probabilities. So I want to associate more to yes. So I would be assigning 0.8 to that, and then 0.2 on the other. And I will do the same. Let's associate more to, okay, I think the preference would be enough. Let's don't do anything with the gender. Okay. Now, as you can see, I have given more preference to yes. Okay. So let's compare what happens when we have an equal I don't need this anymore. And I don't need this anymore. Okay, so let's rerun this. I want you to observe what's happening with the p-value, right? So with this, we have put more emphasis to the s, right? And the p-value is 0.432, right? Now, if we do equal proportion, okay, we don't do anything, so it's like 50-50. Notice what happens to the p-value and the chi-square. So the chi-square here is 1.005, okay? And the p-value is 0.3. Now, let's rerun this thing. 0.223. Okay. The thing is, the more unbalanced, okay, the more unbalanced the distribution between the categories in a contingency table, the more you would get a high value for the chi-square. And the higher value for the chi-square statistic translates to a lower value of the p-value. Okay, why is it so? Chi-square statistic is a statistic computed by getting the difference of the observed and the expected. Okay, so the higher the difference, the larger you will get from the chi-square statistic, and it's never negative. It's at least 0. That's why if you go back to the Wikipedia earlier, the densities for the chi-square value always starts with 0, right? So as you can see, it doesn't go into negative, right? There's always a positive value, either 0 or positive. Now, we said a while ago that this p-value refers to the probability, okay, that the null hypothesis is true after observing a test statistic from our data set. Okay? Do you still follow that? I want to make sure if what I'm saying here is still clear. Hasiba, Grace. Okay, I'm not sure. I mean, I need your feedback to tell me this is still working. Okay, again, we are basing our p-value, okay, on a statistic. The lower the p-value, the more extreme is the statistic we are getting. Or it should be the other way around. The more extreme the statistic, because a statistic could be, other statistics could be negative, extremely negative, or
And what do you mean by extreme?
extreme, very large, very low value for your
Very
statistic.
large, like n, or the range, or what is very large?
It's a very large number, not the n, but this corresponding value. Does it make sense? This is a statistic that we compute based from the data. And the more extreme meaning very high, or it could be very low for other statistics, the more
I'm just checking history, the
lower
failure.
that you will observe the p-value.
Okay, you're just trying to
Because
say
this is
that chi-square and p-value have like an inverse relation, right?
inverse. Exactly. Exactly. That's correct. So they have
I thought you
inverse
were
relationship.
talking about the data sample itself when you said extreme. So I was confused.
Oh, okay. Yeah, sorry about that. Here's the thing. Let's make it a bit more a bit simpler. I have a coin here. you have two options, a head or a tail. Okay? I will tell you, the coin is fair. That is our null hypothesis. The coin is fair because the status of no difference is the status quo. We are assuming that all coin is fair, right? And the alternative hypothesis must be the coin is not fair. Now, in order for us to make a conclusion if my coin is fair or not, we'll have to have data. And where can we get data? We will be tossing the coin 1,000 times. And every result will be recording it, right? We will be recording it. Let's put it right here. The result is this. For the tails, we have 89. And for the heads, we have 901, 911. Okay, so our null hypothesis is the coin is fair. Now, I would ask you, what is the probability that we observe 900 heads under the assumption that the coin is fair? How likely can we observe a 911 heads out of 1,000 throws under the assumption that the coin is fair? Do you think that the probability of that is large or small? Guys, would the probability large or small?
Small.
Exactly. Perfect. The probability is small. Why? It is less likely to happen that you observe 911 heads if the coin is fair. Why? If the coin is fair, then it must be near, okay? It must be near 50-50. Not exactly 50-50, right? But it must be near to it. Now, let me revise the situation. I want you to look at this carefully, guys. Look at it carefully because these are the like scenarios that you'll be encountering in the different statistical methods that you'll be doing. Now let's revise the situation. I have 617 heads and I have 400, 300, 83. Math, is my math correct? 900, 990. Okay, perfect. Now, I would ask you the same question. What is the probability? Is it, you don't have to answer like a specific probability value. I just want to know from you, is the probability large or small? What is the probability of observing 617 heads and 383 tails under the assumption that the coin is fair? Is it a likely scenario when the coin is fair? Yes, right? So the probability must be high. So the probability must be large or high, right? Because it's a likely scenario. Do you follow? So going back here, if the probability of observing this statistic, okay, is 0.22, can we say that the gender preference has nothing to do with or gender has nothing to do with the preference? Can we say yes or no? It means 22.3%. There's a chance. That's the probability of observing this statistic under the assumption that gender Has nothing to do with the preference. Is it high or is it low? We couldn't tell because we need a cutoff, right? Let me answer that question. We can say exactly whether 0.22 is already sufficient to conclude that gender and preference are associated. We need a cutoff. We need a cutoff. And what is that cutoff? That is your level of risk. And that's what we call level of significance. That's what you will see if you look into scientific papers. The alpha value. So this is the alpha value, guys. That is the level of significance. That is the cutoff. That is where you decide whether you would conclude that there's an association between your X or your Y. Okay? And what is the conventional level for that? It is 5%. I said earlier that this is your allowable risk. Are you okay with committing a 5% risk of error? If it's life or death situation, 5% is still high. We can go to 1%. In clinical trials, in anything related to medicine, 1% is the convention. So this is standard for medicine. And the 5% is the standard for other things. Again, this is your risk. This is your allowable error. This comes in so many different names. Level of significance, alpha. But essentially, it just pertains to your allowable risk. Okay, Jeff, what do you mean by that risk? There are two types of error in statistics. Type 1.
Hold on, Jeff, just a
Oh,
clarification.
Please.
You say the 5% level of significance. Does this have a name, or this is p-values we're looking at?
This 5% and 1%, they don't have really names. Those are your allowable risk that you control in your study, in your analysis. But generally, they are called level of significance. Whatever value you assign to them, they are called level of significance, typically. I hope that answers your question. So that could be the name you're looking for. But with specific, like specifically 5, specifically 1, there's no name for it.
So
Okay,
with
great.
5%, 5% the standard, 1% for medicine, then you have to calculate the level of significance for each study, right? Is that what we're getting into?
That's already the level of significance for both 5% and 1%.
Well,
We don't compute it.
that becomes like a benchmark to compare it to,
Exactly. Those are the
right?
benchmarks to compare.
Those are the benchmarks. So then we have to,
Yes.
so for each study, you have to calculate your level of significance.
No, we don't compute them. We assign them.
Assign them. Oh.
Yeah. For example, Grace, you're in the medicine industry, right? You're in the health industry. Your benchmark is 1%. That's your allowable error. So if you want to say that a drug is significantly effective in healing a particular disease, then your computed p-value must be less than your risk. So the p-value.
Okay.
You
Oh,
should
that was
observe.
my question. I was like, are these just standalone, or are we comparing it to the p-value, or what? Or
Oh,
what was the name? That's why I was confused. Okay.
I see.
So level
I
of
see.
significance acts as a benchmark to compare the p-value to.
You exactly.
Okay, thank
exactly.
you.
Yeah, the p-value comes from the data.
Right.
Specifically
That's
from
why I
the
was like, so
data.
then you have to calculate a level of significance if this is something separate from the p-value. That's why that's where that
Oh, I
question
see.
came
I see.
from.
Yeah, yeah.
Okay.
Yep. So why is it so? Let me go into the concept of that. This is really confusing, and it takes really some time to process. So I would I would love it if you would ask me questions, okay, to clarify. Why is it so that we can conclude that there is association if the p-value that we have computed from the statistic is less than the benchmark that we have? Okay, let me show you this. So 5%, that is equivalent to 0.05. Don't be confused with it. Okay? 1%, that is equivalent to 0.01. Okay, let's again look into scenarios, right? I will go back to this types of error, don't worry. Say the p-value that you got from here is this. Okay? So the p-value is equal to 0.22. Your cutoff is 5% alpha. That is equivalent to 0.05. Now, your conclusion here should be there's no sufficient evidence to conclude that preference has association, or preference and gender has association. Okay, why is it so? I want you to think. Why is it that if the p-value is greater, then the conclusion is we lack evidence to conclude that there is association between the two variables? Because it is not. Any ideas from the group? Okay, let me ask you once again, what do we mean by the p-value? What do we mean by the p-value again? It is it is the probability of observing a test statistic or more extreme than what we have observed. Oh God, or more extreme than what we have observed under the null. The AI is really smart. Okay. Then what was observed under the null hypothesis? If we say, okay, that the probability of observing a test statistic as extreme or more extreme than that what that what we have observed under the null hypothesis is 22%. What do you think that means? That means it's not conclusive, right? Because 22% is a lot. If I say that you have 22% of dying if you try this sport, or if you if you if you board on this plane, you have a 22% chance of dying. Is that a lot? Yes. 22% is a lot. It is likely to happen. So there's a high chance that the null hypothesis is true. However, what if your computed p-value is less than 0.05 or less than the level of significance? So what if p-value is, say, 0.003 or 0.004? a very low value. If the probability of observing a statistic or an event, make it generalized, if the probability of you dying, okay, if you do a thing, or if you hop on a plane or in a plane, is just 0.004, which is like 0.4%. Would you risk it? How likely is 0.004? In the aviation industry, it's still a lot. Okay. Just to make things clear, in the aviation industry, the standard it's parts per million. That's how safe the airline industry is. They have one part per million. It's very safe. The statistically speaking, you have high chance of dying any other else aside from an airline. They have an extreme um, safety measure. So here again, let's make just for the sake of example, right? Just for the sake of discussion, it's already low. The probability of observing the event, or technically speaking, a statistic as extreme or more extreme than that, is just 0.004. Then it's safe to say we can risk it now, right? We can risk it now. Okay, that's a very low probability. Then yes, I would conclude we have sufficient evidence to say that there is an association between the two values. That's what we play with statistics. We are playing with probabilities. There's no assurance here, but we have a measure. We have a measure of our risk. Okay, we have we can adjust that tolerance to risk, and we have errors that we will be going back later. What do we mean if we for example concluded that there's no sufficient evidence? Rather, there's evidence to say that association exists, but in reality, we erred. Okay, we have mistaken. So, what are the types of error that we are committing? But before that, was this even clear, or was the example sufficient enough for you to create your own example and ask to me if you have understood it correctly? Grace, Hasiba, this is not an easy concept, but I would invest so much time explaining this. Questions? Questions? Like going back to this head and tails. If the probability of serving 911 heads is just 0.004, okay, under the assumption that the coin is fair, would you still conclude that the coin is fair? Definitely no. If that chance of observing that is that low, but I observed it, then there must be something wrong with that coin, right? You are always inclining to much higher probabilities, right? Do you follow, guys? Let's make another example would be gambling. Imagine I have two cards in here, and you would be guessing, and I'll be giving you a clue. No. I think the cards would be a bad example. I'm not good at cards anyway. But were you able to follow, guys? Please let me know if this example makes sense. Okay, I see Grace. Hasiba, may I know? And don't be shy. I mean, our main objective here is understanding, having a good discussion. So there's a saying: in statistics. If the P is low, the HO must go. Let me write that. Famous saying. If the P is low, lower than 0.05, the HO must go. So Jeff, can I risk more than 5%? It depends on you. If your risk appetite could be greater than 5%,
Jill,
then to be
Jeff, HO is
Yep.
referring to null hypothesis, right? HO.
yes.
Okay.
Yes, HO refers to null hypothesis. I might be jumping here to a topic that should be discussed like next week, but I don't want you to just look into this result and not really understand what it means. So apologies if I have to jump to that topic, but we will be running it again. Okay, so could be that now you can totally process it. Don't worry, we'll go back to it in a more detailed way, better than this. Okay, so this is what you want to always remember. If the p-value is low, HO must go. Okay, so let's go back to coding. Let's go back to that result that we saw. So here, let's make things more crazy. Let's also adjust. I will be copying this. I'll be sharing this to the group, don't worry. Um, I will be putting it here. And let me be crazy and adjust also the gender so that we can put more inclination to the males. So basically what I'm doing here is I'm putting more observations to the male. And let's see. And just like that, I received an error. uh, yeah, why would I forget a comma? I'm reckless. Okay. Now we see that the p-value, well, it's a bit low, but it's not substantial in any sense, right? It's not really substantial. Um, Let me see. I have 183 males in here. Why is it so? No, 1,000. No. This is not what I want to do. What I want to do is there would be more males that would say yes. So that's it. But basically what I've done in here is I also made less females. So 0.6 and 0.4. Let me see this one. It's more proportional now, so the p-value is much higher. It's put more emphasis with the females. Like 0.8 and 0.2. Yeah, let's try this one. More higher p-value in this case. It's like male, female, 0.2, 0.8. So there are more females now. 0.5, 0.5, 0.8.2. More proportional. Yes, no. There are more yeses here. Let's make it more. Let's make it crazier here. 0.95 for the preferences. Hmm. Hmm. Give me a minute to think. Tweaking the proportions here, adjust the number of yeses and no. But what I want to do is to make it more in balance between the responses of females and males. So currently, I put more emphasis to the yes, but less emphasis to the gender. 99.01. Let's see this. Oops. Values. This doesn't make sense because I have 0 in here. Okay, so what I'll do instead of tweaking this is for the actual discussion in chi-square, I will use an actual data set, a realistic one, not this. Well, I can actually do it now, but yeah, we lack sufficient time to do the actual data set, so let's save it for later. So moving forward, maybe I would extend for like 5 more minutes. So let's go back to the slides. Okay. Okay, so that's yeah, that's what chi-square statistic is for. Just a quick recap. We use it to test for association between two categorical variables. Two or more, at least two. We can extend it further into more than two. Now we have median and interquartile range. Um, Median and interquartile range, we can also do this, but with ordinal data. So it's not really necessary that you have like a strictly numerical. So what happened here? We are trying to get the middle of the rank, right? So that's what's happening here. So basically, I've created here a data frame again. Computer for the median. So this dot median is a base function. So it's not a pandas function. It's a base function in Python. And then I just use string literal here to incorporate an expression in my print so that it would change value depending on my input here. So that's what the F is all about, the string literal. And now we have an interquartile range that gives us an idea about the spread. Okay, so this is kind of similar to standard deviation, but it looks specifically uh, between the quartiles, particularly the 25th and the 75th percentile. So here we are computing for the 75th percentile, which is the third quartile. And then here, this is the first quartile or the 25th percentile. Those are just base functions that you can immediately apply to a certain column of your data frame. So that's basically what's happening here. This is a column in your data frame DF, right? So this data frame that we have in here, this is the data frame. We only have one column, so that is the satisfaction column. We're looking for the 75th percentile. And here we are also looking for the 25th percentile, get the difference of that. In order to avoid it being negative, of course, the 75th percentile would be the first here, and then subtracted by 25th percentile. And then you will get the IQR. So the larger the IQR, then the higher the variability. The lower, then, of course, the lower variability between the quartiles. And now we have numerical data. So I think this is where I'll end up until key differences. And then the next meeting, we continue with some examples. So numerical data, oftentimes called also as quantitative data. So these are measured. Typically, the qualitative variables are explained and counted, but the numeric variables are measured. Okay. So we have interval data. The best example for this would be temperature, because with interval data, there's no absolute zero. Zero has another meaning. Remember that. There are two types of numerical data. Interval, there's no absolute zero. Zero has another meaning. And then ratio. The easiest way to remember this is that ratio has, well, this is how I remember this. Ratio has an O. So it tells me, okay, ratio has the one with true zero. Zero means zero with ratio. Okay. It is also in numerical data, but it has a true zero compared to an interval one. So some examples are height, weight, and age. Now, it's quite difficult to think of other examples aside from uh, temperature, if you're thinking of an interval data. But with ratio, it's very easy. Zero height, we're not measuring anything, right? Age in years, zero, you're not born yet. Like if it's absolutely, well, it could be in months, right? But zero is typically interpreted. I'm not sure really. In the health industry, zero, if it's specifically measured in terms of years, you don't just put zero there. You usually put in months. If the baby has not yet reached a year old. Key differences. Measurement level. Categorical data is measured using categories, while numeric data is measured using numbers. Statistical analysis. Categorical data is often analyzed using frequency counts and proportions, while numerical data is analyzed using measures of central tendency and variability. Now, there is a concept called statistical power. Statistical power means the number of things you can do with the data. And the highest, the data with the highest level of statistical power is ratio data. And the lowest, you guess it right, nominal. You can do so many analysis with ratio level, and you can only do so few with a nominal level. So there's a concept called variable transformation, in which a ratio level can be converted into an interval data. And an interval data can be converted into an ordinal data by creating those equivalents. Okay, like for example, if your grade is 91 to 97, you are considered as excellent. You are categorizing it. Excellent, good, satisfactory. You have converted it into an ordinal level. But originally, it was ratio, right? Originally, there's an actual score, but it's easier to assign characteristics to it. That's why in grading systems, you would typically find categories. It is also difficult to differentiate, right? What is the difference between a 97 and a 96? Can you say that they have substantial difference, or they are both excellent? So that's one of the reasons why we have those categories. To categorize, okay, if a student got 91 to 97 or 91 to 100, they're all considered excellent. And they are comparable in a sense, right? So there are those reasons why you want to convert into our lower level. But in terms of statistical analysis, you don't want to do that. You must maintain the level that has the highest statistical power, and that is ratio. Okay? So in data collection, if you're trying to develop a questionnaire, I don't advise you to put the age in ranges and make it interval, right? And then eventually converting it into categories like young, old, or whatever, millennial, Gen Z. If there are no reasons for you to do that, okay? If you don't want to have like a homogeneous script that explains, okay, these people are Gen Zs and they have these commonalities. If you want to use those ages, right, in order to like use it as a predictor in a model for like catching heart disease, it's better to have it in ratio level to see that actual value, because your model would tell you, okay, once you hit say 17 years old, or no, not 17, but maybe 45 years old, the risk of getting a heart disease would increase by this amount every succeeding years. So you must maintain that level. Okay, if you make it in a group, then you are basically assuming that there's a substantial reason to say that those people belonging to this certain range are of comparable characteristic. Okay, so we'll be talking about those when we are already discussing the implementation of the methods. But for now, I just want you to be familiar about this different concepts, underline the key differences between these different data types. And now that's it for today's session. I hope you learned something new. For your practice, I want you to do this. I'll be sharing this to John, and you have to answer this and send the answers to me. Identify if this data is a nominal level, ordinal level, ratio level, or interval level. Okay? I'll be sending it to John. So that's it, everyone. Thank you very much for joining, and I enjoyed the session today very much. I'm sending the file now to John. Minute. So after that, then you can call it a day. Um, then tomorrow, uh, I'll be asking John to give you coding practices for chi-square and for um, descriptive measures. Where was it? Lecture 1, statistics. Okay. So John, you can finish it in 10 to 15 minutes, and then you can just jump out of the session. Okay. It's already 10:15, so 10:30, 10:45. Once you're done with it, then you can go. Okay. Grace and Hasiba, all good?
Okay, thank you.
Yep. Thank you very much. Thank you very much, Grace and Hasiba. Bye bye.
Okay, so are you there, Grace and Jasiba? Hello?
I'm here. Sorry.
Okay, okay, thank you for that. So how was the statistics class? How was it?
Hmm. It's kind of rough.
It is it is kind of rough.
He
So
mentioned like a lot of stuff, but there's really only like 2 to 4 major things, so we probably need to like practice, right? So
there, because statistics, it is about the fundamentals, like uh I don't know if I already mentioned it before. So our analysis, almost all of our analysis depends on whether the characteristics of our data set, that like statistics can tell a lot about the characteristics of the data, about about its distribution, and what does it mean if it is skewed, what does it mean if that is binomially distributed, normally distributed, not normally distributed. So almost all of the stuffs about the characteristics of the data set. And given that this is the characteristic of our data set, how should we how should we treat it? What are the operations that are applicable to it? That's one of the things that are very challenging in statistics. Like for every characteristics of the data set, there are there are so many things that you need to consider. For every variation, you might need to use another way to treat your data. That's the challenge for the statistics. But statistics, it is quite what they call this? It is quite intuitive in the way that when you say statistics, you are interested on the characteristic of the population. But since we don't have so much time, we don't have so much resources to tell what is the characteristics of our population. So we are having samples. So let me have let us browse a little bit about the topics that you have covered today. So these are just the definition of the statistics, its application, and the applications of statistics are so vast that I'm not sure what field don't use statistics. Like on the business alone, almost or not almost all of the businesses, somehow they are using statistics. Even if that is just a small business, even if that is a big business, they are using statistics because statistics can tell what will go wrong, or what are the things that have gone right, and how can we utilize those things that are right. So I saw that you already covered the descriptive statistics and inferential statistics. Actually, your exam, it covers the descriptive statistics. You are just describing your data. Literally, how many are the rows, how many are the columns, what are the columns mean, what how many are the missing values. And descriptive statistics, it just summarizes the data that we have. What's the mean? What are the where what are the modes? What is the median of our data set? How it is distributed? Does it follow normal distribution? So those stuffs. And we have also covered the categorical and numerical data. And as we have told you before, these two things, we should treat them in different ways. And categorical type of data is much harder to handle compared to the numerical data. In the numerical data, I think it is just divided into, aside from continuous and discrete, continuous is being measured, discrete is being counted. It is divided into ratio and interval. Is that part of the difference between the two discussed to you today? The difference between the ratio and interval data type? Under numerical data, we have ratio and we also have interval. So do you know what's the difference between the two? Or not? Ratio versus interval. So I guess this one will be covered on the next meetings because this is just an introduction of the statistics to us. I'm not sure what lab should be performed tomorrow. So maybe let us run some of the codes here, but I will also ask Sir Jeff about it. Like what is the uh, activity that we can perform tomorrow on our lab session? Because this is a beginning of our statistics class. It covers many chi-square test, regression, correlation. This one, the regression, Grace, I think you have mentioned it before that, let's say we have dependent variable. Let's say you have scores. Do you still remember the SAT scores? You have the scores of the students and you have this number of hours of studying. So we can set a hypothesis wherein is the number of hours connected to the scores of the students? Like, can we find a relationship such as the more number of hours you are studying, the higher the grade you can have? In statistics, we can do that using this correlation and linear regression. The A/B testing, the geometric mean, coefficient of variation, and some practices. And I think these are we can have here some. These are identification of the data types. But generally, on the beginning of our classes, at the beginning of your discussion with Mr. Jeff, do you have a specific question that you want to expand about the discussion? The way we do it in Python, it will just follow, but the fundamentals, the knowledge should be established about the statistics. So about the discussion, is there a part of the discussion that you think we need we need time to actually explain it or to discuss it? Hasiba and Grace?
I didn't understand about the p-value.
Oh, the p-value.
Yeah.
P-value. Okay. How about
Yeah,
you?
he mostly just went over p-value and chi-square, and he
Oh.
defined
Yeah,
like a bunch of other
chi-square as
stuff
well.
too, like the different types of statistics, and he went over ratio and interval and stuff like that. But
like
yeah, and then
somehow
he was
the
saying like
overview.
yeah, overview exactly. He just did overview, but tried to do some examples with p-value and the chi with like the coin tossed example and
Oh,
stuff.
okay.
And then he was saying like,
I see.
and then we'd expect it to be low, something if or unless they're extreme.
Mm.
And I was like, I didn't understand what he was saying when he was calling something extreme. Does
Like
that make sense?
the likelihood of this happening. Like I think that's the same example that he used in our class. Like you're given, like this is the scenario. You have a fair coin, right? And if that is a fair coin, there is a 50% of chance that it will be a head and 50% of chance that it will be a tail. So if that is a fair coin, if you will toss it 1,000 times, ideally, in those 1,000 times, 500 will be head or and 500 will be tails. Or not exactly 500, like it is close to half because you have a fair coin and you have this idea that if that is a fair coin, 50% of the time it should be a head and 50% of the time it should be a tail. So
So when
given
he
that
says,
given that
sorry.
scenario, given that this is a fair coin, what is the probability that after 1,000 times of tossing that coin, 950 times of the time, it is always ahead? The probability of that happening, if that is very small, okay, that probability, like given that this is a fair coin and you toss it 1,000 times, 950 is a head, 50 is a tail. So what's the probability of that happening? If you can get that value, that is the p-value. That is the p-value. And it is very small, right? Like if that is a fair coin, the probability of that scenario will happen, like you would get 950 heads and 50 tails only, is very small. If that is very small and it still happen, you would get the idea that maybe it's not a fair coin. Does that make sense?
So when he says extreme, he's saying like extremely, or he's saying when he says
Almost
extreme, he's saying like
impossible.
highly unlikely, not
Yes,
like
exactly.
extreme, like large, like very very
Yes,
large
yes.
extreme. That's
Yes,
why I was
exactly.
like, there's multiple ways to like define
Mm,
what he was
mm.
trying to say.
In that case, when we are talking about the statistics, um, it is context. It depends on the context. Like the word extreme in statistics can be used in different ways. If you are talking about the in the value itself of the data, when we say extreme, it can be defined as very large or very low. So one use of the word extreme. And in the probability, like p-values, probability of something to happen given that this is a fair coin. So when we say extreme, very unlikely to happen. So that's one of the uses. In that sense, when he is discussing the p-value, yes, that's correct case. We said extreme and we said that because this is very unlikely to happen. So somehow that's the idea of the p-value. Okay, let me give you another example. P-value is almost always anchored to the problem. Like for example, um, I think for now let's have talk about the fundamentals. We will have separate discussions about the practices when our instructor covered that area. So for example, you have medicine A and medicine B. And you have these participants. You have 100 participants. And suppose all of these participants have the same characteristics. They are of the same age. Like they are representative of your population. But in the sense that all of them have the same characteristics. Okay? All of them have this almost the same age, almost the same height, almost the same environment, almost the same uh, eating habits, sleeping habits. So generally, those 100 people are almost the same in almost every characteristic. You divided them into two. Okay? 50 for group A, 50 for group B. And you have this medicine A and medicine B. And you are testing if I give them medicine A to every person, like on the group A, okay, on the group A, I will give every one of them medicine A. And I will check what would be their blood pressure. So let me visualize that into an Excel. So it's hard to see it. Like you have group, you have group of, we have a number of people from which has, wait, my Excel is not working the way I want it to work. We have group A, which will receive medicine A. And you also have group B. Group B. And they will receive medicine B. You have 50 participants for each. So they should be 1 to 50. 48, 49, 50. The same way as group B, they have 50 participants. And remember that these participants are almost the same in almost all characteristics. So on group A, after you give this person a medicine, you recorded their blood pressure. Let's say 90. This person is 92. This person is 98. This person is 99. This person is 97. This person is 97. On group B, you gave them the medicine B and you recorded you also recorded the blood pressure 89, 99, 98, let's say 100, 98, 97, 95. Oops. Let's do this 95. Now you have this question, you have this hypothesis in mind. Hypothesis. You are interested, not hypothesis, problem. You have this problem. You want to determine that the blood pressure, the average blood pressure of group who received or who took med A is the same as the average blood pressure of those people who took medicine B. So in that case, you will calculate for this average. So let's say this the average of this is 95. And this is 96, or let's say 98. So you want to determine if the average blood pressure of this group is the same as the average blood pressure of this group after they took medicine A and medicine B. So if they are the same, if the effect of medicine A in blood pressure is the same as the effect of medicine B in the blood pressure, the difference should be almost close to zero. If that is true, if A is equal to B, the difference should be almost zero. We are not saying it's exactly zero, but it should be close to zero, right? If that's the case, they should be close. And in statistics, we have a way to test it. Like, what if the difference is 10? Your difference is 10, or the difference between the averages is 20. Like, let's say, this is 90, this is 100, or this is 80, this is 100. So we have a way to test that what's the probability of that will happen. That they are, we are thinking they are the same, but the difference is that this is 100, this is 90. So since this is a probability, you would get a p-value. You would get a p-value again. And if this p-value is very low, if this p-value is very low, like less than 0.05 or 0.01, therefore we can conclude that they don't have the same averages. At least one of them is higher than the other. So the research process looks like this. This is your problem, and you can translate that into hypothesis. You have the null, and you have alternative hypothesis. Your null hypothesis goes like this. The average BP of group A, like I will just, you can write it in full sentence. You can also write it in symbols, but let's write it in symbols. Average BP of group B is equal to average BP. Commonly, null hypothesis is they are equal. That's our thinking, that they are the same. But for the alternative, we can say that average, okay, is not the same. We have different ways to write alternative hypothesis. We can say that the average of the group A is higher. Okay, we can say that. We can also say that the average of group B is higher. So like this. So we have three different ways to write alternative hypothesis, but commonly, this one, this not equal. We are not interested who is higher, who is lower. We just want to determine that they are not equal. So there are those type of problems. Here we are interested only whether the average blood pressure of these two groups are equal or not. So in our problem, we can write this. And the process is we will compute for the p-value. And this is, you will not compute this manually. Using the correct test, it would give you a p-value. Like in this test, the test appropriate for this is, since these two groups are independent, meaning they are separate groups. So we can use independent A/B testing, independent t-tests. T-test is the statistical test that we can use. But the nature of the problem is you are comparing two groups that are different from each other. They are distinct from each other. group A people are different from group B people in the sense that they are different person. People who took medicine A is not the same as people who took medicine B. They are separate group. So if you do these tests, automatically it will give you p-value. Okay, and let's say this p-value is 0.06. Let's say 0.06. So you would get hold of this. You will hold that value. Now you will ask, what is my level of confidence? What's my confidence level? If you want to test this at 90% confidence level, or let's say, what do we mean by confidence level? So whatever findings that you would see, you would say that, okay, I am 90% confident that they have the same averages. You can increase the level of confidence. You can say 95% confidence level. I am 95% confident, or we can say that 95% of the time, this is the thing that will happen. That even if we replicate this experiment 100 times, 95% of the time, this will be the result. Okay? Or 99, even 99%. 99%. 95, this one is 99%. Okay, this is harder. This is a very hard claim. Like, if you replicate this experiment 100%, around 100 times, 99% of the time, this would be the findings. For example, we determine that, okay, they are just the same. And we use this 99% of confidence level.
Hold on, John. Can you go back for a second? Because I'm having to like hold it in my head. So with the
Okay.
p-value of 0.06, which hypothesis do you say is correct, the null or the alternative?
It depends on the confidence level. These things, this confidence level, they corresponds to a level of significance. If that is 90%, your level of significance is 0.1. If that is 95%, your level of significance is 0.05. If that is 99% confidence level, that is 0.01. This is the level of significance. Actually, let me repeat the process. First, you have the experiments. Right? You have this data that are recorded. You have the averages, and you are asking this problem: is the blood pressure of group A equal to the blood pressure of group B? Given that they took this different medicine A and medicine B, and our goal is to determine which of this medicine will induce higher blood pressure. So actually, that's our problem. So with that problem, we come up with two hypotheses, null and alternative. Our null is they are equal, and our alternative is either of these three. You can just choose one depending on the goal of your problem. Okay? And with that, after you have this null, you will set how confident you are. How confident do you want to become on whatever result you would get? You can have 90%, you can also have 95, you can also have 99%. These are the common three, but there are also other confidence level. Okay? But each of them corresponds these values. But take note, this 0.1 just translate to 10%, right? This 0.05 just translate to 5%. And the 0.01 just translates to 1%. And they are partner. 10% plus 90% is 100. 95 plus 5% is 100. 99 plus 1% is 100. So these things are just translated into its decimal versions. Like 10% is 0.1. And then you will now proceed to the proper testing or the formal testing. Okay? And suppose you have chosen the correct test, you have analyzed its characteristics, and you have determined the correct test, and you have applied it. Automatically, it will give you a p-value. Now, what's the use of the p-value? Suppose you are creating an experiment with 95% confidence level. So take this note in your mind. What's the level of significance? 0.05. That's the p-value, 0.06. So what is the thing that we want to determine here? If the p-value is greater than the level of significance, reject the null hypothesis. Okay, let's take it slower. You created an experiment and you set the confidence level to be at 95%, and you know that its level of significance is 0.05. Now you calculated the statistic and you got this p-value 0.06. So how can we use this information 0.05 at the confidence level and 0.06 there at the p-value? So this is always the case. This is almost always the case. If the p-value is greater than this value, reject this. Okay. Question. Do we reject the null hypothesis here or no? Let me type here the CL or level of significance. The level of significance is 0.05. This is 0.06. Who is higher? The p-value, right?
Mhm.
Okay. If the p-value, it says that if the p-value is greater than this, reject the null hypothesis. Who is the null hypothesis? This. You are saying that they are just equal, but we are rejecting that. Therefore, this is the true thing. They are not equal. Okay? That's the case here. So, key takeaways here. You should, number one, let me have here text box. Text box. Number one, the problem should be clear. How can we tell that the problem is clear? If you can translate it into, this is my own observation only. Okay? The problem is clear if you can translate it into a hypothesis that are clear. Hypotheses that are meaningful. Look at this. The problem is this, right? And we have a way to clearly translate that into null and alternative hypothesis. This should be translated into null and alternative hypothesis. Okay? Number two, your hypothesis should be clear. Is our hypothesis clear? Like, for example, null hypothesis. Is it clear? This one is clear. We are saying that the blood pressure average of those people who took medicine A is just equal to those average of people who took medicine B. So it is clear, like if you will somehow translate it, we can um, understand it. So the hypothesis should be clear. Number 3, level of significance should be defined. The level of significance, so for example, test it with 95% level of confidence. So you will know that the level of significance is this. So somehow this is a cheat sheet that I'm giving to you as early as this. For Sir Jeff, it's he says that it's okay if we will be a bit advanced. Like we will have some snippets of the things that are outside of the things that are discussed today, because it will help establish the knowledge the next time that we saw it. But there are others that don't want it that way. Like let's just stick to the discussion. But in our case, it's okay that we have this information. So we should have the level of significance. And I think it's already 11, but um, hold on for just a couple of minutes. Number 4, select the appropriate test. Select the correct test. The p-value will follow. Okay? You should be more concerned of the test that you are using than the p-value. Every test will give you a p-value. That's the thing in statistics. Every test, it will give you a p-value. But that p-value will not be useful if the test is not appropriate. So suppose we have selected here the correct test. So it gave us a p-value. So number 5, if the p-value is greater than the level of significance, the one that is defined on number 3, if if the p-value that is a result from the number 4 is greater than the level of your significance, reject your null hypothesis. If you will follow this structure on your experiments and hypothesis testing, you would not be confused on where to look, because you have this structure that okay, my p-value is greater than the level of significance. So what does it mean? I will reject my null hypothesis. What is my null hypothesis? It is clear already on the number 2. You just need to look at it. And additional on the number 5, translate the decision into words. Like the average blood pressure of people who took medicine A is not the same as the average blood pressure of the people who took medicine B. Does that make sense? Like, did that somehow clarified some of the things about the uh, flow of the experiments? P-value, you don't need to dive very, very deep into this. It just explains that the probability of something happening. Like, what is the probability of having this result, given that you said they are the same, given that you said they have the same effects, or given that you have a pair coin, what's the probability of this thing to happen? That is very low. So if that happened, somehow there's a problem in our claim. Okay? So this is also heavy. The introduction of the statistics is heavy, and I think I gave you also a heavy stuff in this. But that's the analogy. Not an analogy, but quick, simplified process of generally the test that we have. Let's say your problem is correlation. Your hypothesis can be written in this way. Correlation, you are talking about the relationship between two things. Null hypothesis, variable one, or let's say age is not related to um, age is not related to average salary. And then the alternative age is related. So something like that. Typically, we are putting the no difference, no relationship under the null hypothesis. Okay. So null and alternative, you can write it depending on the problem that you are solving. If you are interested in the correlation, therefore your problem is these two variables connected, related to each other or no? Or no? Okay. So I hope somehow that gave you additional information. Do you want to add something, or do you want to have any questions or clarifications? But if not, I think we can still continue on discussing this tomorrow.
John, can you please send the module I couldn't find in the
Okay,
Canvas?
sure.
And a screenshot from your explanation, please?
This one.
Yeah.
Oh wait, where is it?
Th-
This one. Okay. Or I will send this file to you, to the statistics. Statistics. What is this? Research process. This is the somehow research process. That is the process, like those 1 to 5 items that I gave to you. Generally, in every experimentation, that is the process that we have. And it also helps us to identify what's the tests that you need. I will send these things on the Discord. So let me know if you can access it or you can access it. Yours is IDA April. With that, any questions or clarifications? Concerns? Or any additional insights? Where is our class? This one. We'll send this file to you, lecture 1 statistics, as well as the one that we have used today. For now, please take your time to read through and understand the statistics, first parts of it. I will communicate to Sir Jeff to talk about what is the possible lab that might help you to further understand the concepts. So if you don't have any questions, we can call it a day.
All right. Thank you, John.
Thank you. Thank you, Grace. Thank you, Hasiba.
Thank you, John. Have a good one, John and Grace. Bye.
Thank you.